So this is the card that you think are weird. Last night for test so, but not that one. There's one from your
Okay. Let's continue where we left off. The recording, if you ever go back to watch the recording, it might look weird. There is a section in my screen that is fixed from my email. So it might show you the presentation with part of my emails. So I don't know why that's happening. Anyway, what is simplification value used for? So try to remember, it was the last thing, one of the last things we worked on. Yes. Average molecular weight. So simplification value is kind of a characteristic test, unique. It is a value that is unique for different types of oils, and it helps us use this value to calculate an average molecular weight of triglycerides and fatty acids. So if oil A, I don't think we covered that as part of the calculation question last time, but let's think about it together. And I will write up the equation again for you to think about it. Remind you of the equation. You have triglyceride. It reacts with 3 KOH molecules to give you the glycerol plus 3 fatty acids. Yes. And then the saponification value is really the milligrams of KOH to saponify 1 gram of triglycerides. So X milligrams of KOH that would saponify 1 gram of fat. So, and then you have 1 mole here reacting with 3 moles. Okay? So the molecular weight, so grams per mole, X grams per mole reacts with 3 times 56.1 grams per mole. All right, looking at all of this, if oil A has higher saponification value than B, which one has lower average molecular weight? A or B? Think about what number of moles means the molecular weight, or the molecular weight is grams per mole. And then think about this much saponifying 1 gram of fat. So if you have large molecular weight, that means you'll have less number of moles in 1 gram. Does that make sense to all of you? If the molecular weight is higher than another molecular weight, that means you have less number of moles in this 1 gram sample. Does this make sense to everybody? If it doesn't, let's clarify. So I expect that it makes sense to everybody. With this knowledge, then tell me if oil A has higher saponification value. Does that mean that it will have lower or higher than B? Think about it, take a moment, and tell me. Any brave soul? Anna?
Just lower.
Yes, it is lower. Can you explain it though?
I don't know. I used the equation from last time and just plugged in a smaller value.
If you just use the equation, if you just use the equation, that is true. But if you think about it that way, so the milligrams that you want to saponify 1 gram of fat, it will be less if the molecule is larger. Okay, if the molecule is larger, you will have less molecules, less number of moles in 1 gram, so you need less KOH to saponify that molecule. Okay, or these number of moles. Right? So if you have large again, I'm going to repeat that. If you have large molecular weight, then you will have less number of moles in 1 gram. If you have less number of moles in 1 gram, you will need less moles of KOH to react with that 1 gram. Okay? So higher saponification value is associated with lower average molecular weight, and the opposite is true. Think about it in a sense of a large molecule, large molecular weight, that means you have less number of moles. With less number of moles per gram, you will need less KOH to saponify them. Okay? Because saponification, it has to do with how many molecules you need of KOH. You need 3 molecules of KOH per 1 molecule of triglyceride. If you have less molecules of triglycerides because you have larger triglycerides, then you would need less of that. Okay? Think about it that way, but as Anna solved it, another way to think about it is where is it in your equation when we calculated the average molecular weight. It's in the denominator, so a larger value in the denominator will give you a lower molecular weight, and a smaller value will give you a larger molecular weight. Okay. Which test is used when testing efficiency of hydrogenation? So with hydrogenation, what are we doing? We're breaking the double bonds. We're saturating your oil. So which of the methods we talked about last time would be a good test to do to determine efficiency of hydrogenation? Yeah? Iodine value, thank you. Yes? Presence of free fatty acid is an indication of what? So if you're measuring your oil, and then whatever that oil is, you measure it and you find high levels of free fatty acid. What does it mean? It can mean many things. What's that? Okay, yes. It means that the oil potentially is not refined. What else? Rancidity, hydrolytic rancidity. So you could have had some breakdown of triglycerides, potentially due to presence of lipases, or if it's a frying oil, due to breakup of the triglycerides during the frying at high temperature and presence of moisture from the food. Name few physical characterization tests. We talked about several last time. So physical characterization tests that are indicative of or unique to the different types of oils. There were stories associated with some of them. Yes.
Smoke point and spark.
Yes, smoke points, spark points, igniting points, and then the fire point. And then there are, to test winterizing, we can do cold test and the cloud test. Other tests, refractive index, solid fat index. Well, it's not necessarily a test for oils. It could be test for fats, like margarine or butter, because butter does have 20% moisture. Yeah. And it can also be the test for partially hydrogenated oil. Yeah. Good. Moving forward. So let's talk about oxidative status. We have the present status of oxidation, and then we have looking at oxidation over shelf life, determining the stability of your oil or fat, or the stability of a product that has high fat content over time. So peroxide value is one of the very common methods to determine the current status of oxidation. And it is a measure for the primary oxidation product. So peroxides are primary oxidation products. So they are among the first products that are formed during once liquid oxidation occurs. So it is defined as milliequivalents of peroxides per 1 kilogram of sample. Okay. So this is a peroxide that is formed due to oxidation, presence of oxygen. And if you have a peroxide, it can react with potassium iodide. And this reaction is going to give me iodine. Okay. So if I produce iodine, that means I have peroxide. If I don't have peroxide, I won't produce iodine. If I produce iodine, I can determine the amount of iodine produced. If I add starch, it will be blue. And I titrate with sodium thiosulfate at equilibrium. At the end of the reaction, when all of the iodine reacted, then we get a colorless endpoint. Now, also note here that it is sample minus blank. We run a blank to account for any peroxides that come from reagents we've used. But if you don't have peroxide, you won't generate iodine. So the sample would you expect to have more peroxide than your blank, okay? Unless you don't have any, and then it will be 0, okay? So that's why in this case it's not blank minus sample, it's sample minus blank. Okay? Now it's milliequivalent. So at equilibrium, milliequivalents of iodine will be equal to milliequivalent of sodium thiosulfide. So we are dealing with milliequivalents. So in this case, we do not divide by 1,000 because we don't need to convert milliliter to liter. So we don't have a division by 1,000. So we divide by the weight of the sample. That will give me milliequivalents per gram. And then I multiply by 1,000 because I need in 1 kilogram. So the multiplication of 1,000 is to give me milliequivalents per 1 kilogram. And because I'm dealing with milliequivalents, not number of moles, I'm not calculating mass, something else is missing from this equation, and that is the molecular weight. Okay? So there is no molecular weight of iodine here. Okay? There is only the normality and volume of the titrant, whatever we're titrating with, and then there's no molecular weight because it's milliequivalent. We are not determining mass, we're not converting number of moles to mass per molecular weight. So if you look at the equations we had before, you had the molecular weight of iodine because we're looking for mass or grams and 100 grams for iodine, for example. Here we don't have that. So you need to understand the equation. If you understand the equation, you will remember it on the test. So when I say peroxide value, you will remember the equation and you go, oh, the units are milliequivalent per 1 kilogram. So there is not, it's milliequivalent, so there is no division by 1,000. It's milliequivalent, so there is no molecular weight. And it's multiplied by 1,000 because it's in 1 kilogram. If you remember the unit, it will be easier for you to remember the equation. So you'll be doing peroxide value in the lab. I forgot one thing on this slide. It is a primary oxidation product. So a freshly refined oil or fat will have a peroxide value of 0. Freshly refined, and they are just you're measuring them as fresh oil or fat, so you shouldn't expect any oxidation. What do you think the peroxide value would be for a very rancid oil? Very high, right? Really high, like rocket high. Yes? Who agrees it's going to be really high? Hayden is very Regina is. Anybody else? So who disagrees? And the rest of you, you have no opinion? No, I want each one of you to have an opinion today. Very high or not very high? Let's do it again. Very high value of peroxide. Okay, few courageous souls. Not very high. Alex. Hi, how are you? Okay, those of you that said hi, can you explain it to me, Brigida?
Well, high recidivity meaning there's high presence of oxygens, therefore there will be more peroxides present, and then more production of iodine, and then high titrant is needed to convert through to others.
I mean, this makes sense, what you're saying, but it's not true.
Okay.
What did you want to say, Paige?
Well, I'm just curious, well, like, which one's brighter, or are you getting to that point?
I'm getting to that point.
I just,
What do you think?
I just disagree.
Disagree with what Brigida said?
I think it's low, but more because peroxide is like your first primary product. And so, like, if you're this far in like rancidity, like your peroxide is going to be used up to make your secondary products.
Thank you. Yes, correct. Does that make sense to you?
Sorry.
Yes.
Sorry.
No, it's good. We are having a discussion. So we do start with a very low peroxide value. So you're going to plot peroxide value over time of storage of oil. So you have your peroxide value here and you have time. So if the oil behaves, and usually oils don't behave, but if they behave, we're going to start with very low concentration of peroxide at time 0. Okay, so it's going to, and then over time, yes, we are generating your peroxides, but at the same time, peroxides are not stable. They're going to be oxidized further into secondary oxidation product. So at the time, you will reach a peak, and then the production of secondary metabolites will be more prominent than the development of peroxides. So we start seeing going back down in peroxide value, because the rate of production of peroxide will be high here, but then it starts to decrease here as more and more secondary oxidation products are used until all of your oil is oxidized, all of your primary oxidation products are converted to secondary oxidation products, then you go back to 0. So this is very, 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 very rancid oil. And this is very, 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 very fresh. Now, are the oils that we're going to work with are very, 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 very fresh? I don't know. I don't think so. Yes.
How do you like determine if it's like rancid or fresh just based on this? If they're the same?
Yeah, how would you determine? If you measure peroxide, you got 0. Are you going to be confident? Are you going to say confidently this is a fresh oil? What would you do? What would
Really rancid, have like obvious sensory.
will be really, really bad
Really
smelling. So why don't you open it up and put it close to your nose and you're going to go, ooh, this is really bad.
But I guess,
Huh? Yeah. Huh?
but I guess even to that though, how would you know on either side of the curve? Like,
Yeah, you wouldn't know unless you actually store it and see what happens.
and then see what happens afterwards. Okay.
Yeah.
So for the two bottom.
Yeah, but here, let me tell you, if it's here, it's going to smell more than it's here. Primary oxidation products don't have much correlation with sensory as secondary oxidation products. For example, secondary oxidation product, one big one is Hexina, and it really smells very obvious. So if you're here, you're going to smell something until it really smells bad. Okay, all great, good. So, other ways of measuring current status is determining the anisidine value. Anisidine is really a reagent, and this reagent or with aldehydes. Aldehydes are secondary oxidation products. So when they interact with aldehydes, you get a chromogen and you measure the absorption at 350. Totox value is a combination of measuring secondary oxidation product and primary oxidation product. So Totox value is often used to get more accurate status of your oil by combining the Einstein value that measures secondary products like aldehydes and then a peroxide value. And then you get a Totox value that will give you a status of your oxidation. So here's an example. If you have soybean oil that is relatively fresh, it will have less than 2 Einstein value and Totox value less than 4. It's kind of like, there are values for different oils like that. So Hexina, yes, Anna?
How fast are like primary react products turned into like secondary products?
It all depends on the conditions under which your oils are stored. So there are so many different factors that impact that: the availability of oxygen, the availability of light, the temperature. And so it really depends on all external environment factors. So the rate of reaction is dependent on environmental factors. It also depends on how much you're generating peroxide, which is dependent on polyunsaturated fatty acids. So if you have more polyunsaturated rather than mono or saturated, you won't have as high of a rate as well. So you have environmental factors and also endogenous factors such as the saturation status of the oil. Also, another important factor is how many free fatty acids you have, because free fatty acids are more prone to oxidation than esterified in a triglyceride form. Okay, so many factors. Okay, Hexina is another secondary oxidation product. It's one of the volatiles that can be produced. So you can have pentane, pentanal, hexina. Hexina is the most common one that is usually tested and correlated to secondary oxidation products. And also, it correlates really well with sensory. We're saying that you can actually smell it. How do you test Hexina? It's a very simple method. It's a GC method, and we call it headspace because sometimes you don't need to do any sample prep. So you put your oil in a container and you close it, leave it there, then the volatiles equilibrate between the sample and the headspace above the sample, and then you can take a needle and withdraw some of that headspace, the volatile material in your headspace, and inject it onto your GC. So it's very simple. You can run it and determine Hexina. So lipid extraction is not required. So you can also put a flour sample as is. If you're looking at lipid oxidation in a grain flour, you don't have to extract the fat. Also, these are volatiles, so you can put them, leave them to equilibrate in the container, and they will volatilize above the sample. Okay, this assay is also a very common assay. We call it T-bars, and it stands for thiobarbituric acid reactive substances. So these reactive substances are mostly melanaldehyde. So the melanaldehyde is very specific secondary oxidation product that will react with thiobarbituric acid, or TBA. Thiobarbituric acid, and then gives you a chromogen that will absorb light at 530 nanometers. It also correlates well with sensory evaluation, as it can have odor. So it relates odor and taste. So it will relate to sensory evaluation. However, this method is not as accurate as using HPLC because the melanaldehyde can react with other components and might not react with the TBA, might not give you accurate measurement at 530. So there is an HPLC method for that as well. Another drawback, it is a derivative of specific linoleic acid. So if you have an oil sample that is not high in linoleic but high in linoleic, for instance, so you won't get as much malonaldehyde, but you get other secondary products. So if you're just doing T-bars on an oil sample that is high in linoleic but not high in linolenic, you're not getting accurate determination of the oxidation status. Okay, moving on, let's talk briefly about measuring the stability. So looking at oxidative stability, and this is often done in industry to determine the stability of the oils in general, so that they know how they can use shelf life and everything, but also it's very commonly used if you want to determine the effectiveness of an antioxidant that you use. So you add your antioxidant, and then you would have a control without an antioxidant, and then you determine if the antioxidant is going to help in extending the shelf life. That's one thing. Also, there is a synthetic antioxidant versus natural antioxidant. You want to test, can the natural antioxidant compete with the synthetic and replace it in an ingredient list? So these are real important tests that we need to do sometimes as food scientists, not just to predict shelf life, but also determine the use of different ingredients, the effectiveness of the use of different ingredients. So the way we do that, we go with accelerated shelf life studies, because when you want to determine shelf life, you want to do it as quick as you can, rather than store it at room temperature and under not abused condition, then it'll take a long time to make a decision. So we call them accelerated shelf life because you kind of induce the oxidation or provide the conditions that will make it go faster, and from there you can predict shelf life. Okay, so we have 3 different common tests that are usually done. The most common one is really the oven storage test, where you store your samples at elevated temperature. It says in your book, it says the most common one uses 60 degrees, but we can do different. What do we do for the lab, Cindy? Yeah. 185 degrees C? Well, that's very, very abused. That's very, very accelerated. That's a very quick one. Okay, so what you do is you put your oil sample. Alex, would you like to share with us anything? Okay, so keep it low. If you want to talk, if you have a conversation going on, you can just leave the classroom and have your conversation outside. Otherwise, keep it very low so that it does not interfere with anything. No? You're not talking? Who was talking? My eyes deceived me. Okay, you're not talking. Okay, so going back to this, what happens here, what we're trying to determine is something called the induction period. That means the time it takes before your oil starts oxidizing. So what you would do is you would store your samples at elevated temperature, and you pull out samples every week, 2 weeks, or every few days, depending on the temperature that you're using, and then measure lipid oxidation. Oftentimes you can measure peroxide value if you know that you're starting with a very fresh oil. So you can measure peroxide value. And then you would determine the onset of oxidation. That means the time you start detecting peroxide value. You'll notice in the lab when we do it next week, not all oils start at 0. Because we get oil that is stored in the on the shelf in the supermarket. We don't know exactly how fresh that oil is. So we might have some peroxide already in your sample before we start measuring. Okay, so that's the oven storage test. So you increase the temperature and you monitor peroxide value over time. The oil stability index is another method that can be used. So you get your oil and then you put it in a bath at 130 degrees C, it's usually an oil bath so that you can get to that high temperature. And what you do is you boil either air or oxygen directly in your oil sample. So you're giving it a lot of oxygen and then heat. So you're basically inducing oxidation to happen. And then what you do is once oxidation starts, you get volatiles that will leave your sample, and we kind of collect them into a water container, and then you measure conductivity in that water. The last one is oxygen bomb. So it doesn't mean that we blow anything up, but it means that you put your sample in a pressurized compartment where you pressurize it with oxygen. And then you put it in a boiling water bath. So your sample is in that compartment that's pressurized by oxygen. And we put it in boiling water, and then we monitor the drop in pressure. The drop in pressure is an indication of uptake of oxygen. Okay, so these are the three different methods for measuring stability. So lastly, we'll talk briefly about characterization of the fat by looking at the different fat components or lipid components, whether they are free fatty acid, mono, di, or triglycerides, polyunsaturated, monounsaturated, or trans, phospholipids, cholesterol, or lipid-soluble pigments and vitamins. So these are the different lipid components or different lipid fractions that we can look into. Mostly, we use GC methods, sometimes coupled with MS for identification purposes. And if we're doing screening, we can do thin layer chromatography, just if we're just screening what different types we have, qualitative measure. Often, or sometimes, you want to analyze a sample that could possibly contain cholesterol, which is the fake fat. That means 6 fatty acids associated with sucrose. They don't have caloric, they're not digested, they don't have a caloric value or impact. But it's in your sample and it is with the oil fraction. So in order to remove it and just analyze the fatty acid component, what you would do is you would hydrolyze the triglyceride by lipase. And so the lipase will break triglycerides and give you free fatty acid, whereas cholesterol will not react with lipase. Okay, so when the fatty acids are produced, they are usually precipitated by calcium to form calcium fatty acids, and then olestra is extracted and removed, and then you can proceed with the analysis of fatty acids. Okay. So the analysis of fatty acids, we already covered that. You've done the framing, where you determine the composition of the fat or oil. You also determine adulteration, like you did in the lab. For cholesterol, it's a non-saponifiable matter. So you remember when you were determining free fatty acid, you had to saponify your triglycerides, and you used NOH with methanol, methylated NOH. But the cholesterol, if it's there in your sample, it won't be saponified. So what happens then, you solubilize your fatty acid, turn them into salts, and then they will be in your non-organic phase, and then the cholesterol remains in your organic phase, and then you can take that and analyze, derivatize it so that it can be analyzed by GC. Finally, this is just a thin layer chromatography, qualitative method. You have silica gel as the adsorbent, and hexane diethyl ether formic acid as your mobile phase, and then you run standards, phospholipids, monoacylglycerol, diacylglycerol, free fatty acid, triacylglycerol, and then your sample. And then you can determine by running standards, you can identify what you have in your sample. But again, it's qualitative, mostly qualitative. Okay, so what you'll be doing next week in lab, you're going to run saponification value, iodine value, and peroxide value, as well as free fatty acid. And then each group will have a type of oil. These are the different oils. The olive oil will have two types of olive oil, the virgin olive oil and the refined olive oil. So we will determine peroxide value on fresh and stored samples, and then you're going to plot your peroxide value plot over time. You're going to determine the authenticity of your oil samples by comparing the saponification value and iodine value to standard references. You're going to determine free fatty acid content and determine the impact of free fatty acid on the peroxide changes in peroxide over time. And then you will, it's going to be a full lab report, so you'll be sharing the data and talking about the different oils. Okay, so I have a few minutes, 9 minutes. I'll start a different. I know you don't like me right now, but I have to keep going. Protein separation and characterization. So far we did carbohydrate characterization, fat characterization, and now protein characterization. How can we separate protein, whether separating them from a complex food matrix or whether separating proteins among themselves? You have a mixture of proteins and you want to purify different types of proteins. Can we separate them based on solubility, adsorptivity, or denaturation? All of the above. It's the safest answer and the correct answer. Yep. So all of the above, different proteins have different solubility at different pH. Proteins might be soluble at alkaline pH, while starch is not. So you can separate proteins from a starchy material. You can separate based on adsorptivity, whether based on charge, like ionic exchange chromatography, or based on hydrophobicity, interaction with the hydrophobic media. So you can do that. And then you can separate them based on denaturation. So you can denature the protein. Let's say you have a sample that has casein and whey. Whey protein can denature at much lower temperature than casein. So you can bring up the temperature high enough to denature the whey protein, and then the whey protein will precipitate, whereas your casein will remain in solution. So you can use denaturation to precipitate your protein. If we have different proteins in a solution, which method you can use to separate them from each other, like a mixture of protein? Thank you, Anna. Anna's going to go with all of them. Again, the safest and correct answer. You can separate proteins based on size, because proteins have different sizes. You can salt them out. Some proteins have different charges. So at low concentration, one type of protein will be precipitated because you shield the charges of that protein, while another one has a lot of charge, needs more salt to shield the charges and precipitate it. So you can actually salt out all the protein you have in the sample and separate it from sugars, or you can change the concentration of salt gradually to precipitate one type of the protein after another. Electrophoresis, gel electrophoresis, we'll talk about that. So you can separate based on size, based on charge, and then also based on molecular weight and charge as well. So all of this. So here we're talking about protein separation and then characterization. Before we get to characterization, why do we care about separating protein? Why is it important or relevant? Think about from an industrial perspective, from analytical perspective. Okay.
Purification. So like nutritional claims that you want to make or health claims.
So you're mixing two concepts together, I feel.
Like I said.
First one, purification. So production of protein ingredients. So let's say producing whey protein isolate or soy protein isolate to be used as ingredients in different food applications. So the industry uses a lot of different techniques to produce different isolates, protein isolates, to be used as ingredients. So, okay, ingredient production. Anything else you can think of? We covered last week a subject that's very important. We utilize something, yes, Rumi? Allergenicity. To determine allergenicity, yes, you can separate the protein to determine its allergenicity by immunoassays. Yes, that's part of isolation to characterize the protein. But I was talking about last time enzymes, right? Use of enzymes in food analysis. Enzymes are proteins. So we need to isolate these enzymes, purify them so we can utilize them in our assays, whether an assay to determine a certain constituent or use them as processing aids. So we need to isolate them and then use them. Okay, so production of food ingredients, purified protein for further analysis, where you want to study a new type of protein that from a new crop, for example, like Laura's doing with hemp. So you want to extract that protein, determine its functionality, determine its nutrition. You have to take it out of the matrix to study it. Or you want to isolate it in an analytical assay if it's an enzyme that you're using in an analytical assay, or a substrate for an enzyme that you're trying to determine the activity of. And to determine the impact of processing and changes in structure. So what I mean here is that when you produce protein ingredients, there are so many different processing steps that you can do to produce this ingredient. And that processing step can impact the structure of the protein, might denature it, make it not functional or lose digestibility, lose bioactivity. So we isolate that protein after different processing to determine which processing would be the best that would preserve the protein. Okay. So proteins are very unique components in food, and they vary in many different characteristics. They vary in their nutritional quality because of amino acid composition and digestibility. They vary in their functionality. Some proteins are more soluble, some proteins form gel, some proteins can mimic meat by texturizing them. So they differ in functionality. But what we care for here in this topic is the biochemical differences in the proteins, which we will use for separation, understanding their biochemical differences that we will use for separating these proteins. And with that happy note, I'm going to stop and continue next week.